Welcome back. Today we're going to be talking about areas of regular polygons. So we've dealt with regular polygons for a while. They're equilateral and equiangular. And some of them we've encountered more often than others. In the real world, the one we'll encounter the most is obviously a regular quadrilateral, which is more commonly referred to as a square. We have a very basic formula for the area of a square. Since a square is a rectangle, the area is the product of the base and the height. The base and the height are the same, so the area of your square is the side length squared. I honestly hope that's not new for anyone, and I hope that was easy enough for you to follow. The second most common regular polygon that we encounter is a regular triangle. So a regular triangle is equilateral and equiangular. So all the side lengths are the same, all the angles are the same. I'm just going to call the side length S. Now the area of a triangle in general is 1/2 base times height. So for this triangle, the base is any of the sides, so that's going to be S. And now we just need the height. I'm just going to use this S as our base and draw our height like that. Now our height is an altitude, and if we think back in a regular triangle, the altitude is also a perpendicular bisector of the base. So this is S over 2. And the altitude is also an angle bisector of the vertex angle. So that's 30. This is already 60. That's 90. Oh, look, it's a special right triangle. The short leg is S over 2. The hypotenuse is twice that. And the long leg is root 3 times that. So it's S root 3 over 2. So that's our height. So if we simplify this, the area of an equilateral or equiangular triangle, S times S is S squared, root 3, and 2 times 2 is 4. This formula works anytime you're finding the area of an equilateral triangle. S squared root 3 over 4. Every single time it'll work out nice. So you don't even need to go and derive your height. If you just know the side length, it's S squared root 3 over 4. So that's regular triangles and regular quadrilaterals, but those are not the only regular polygons. We have infinite other regular polygons with any number of sides. I'm going to just work with a pentagon, which is the next one we haven't talked about, but what we're going to derive from this pentagon is going to work for any regular polygon. So it's a regular pentagon, all the side lengths are the same. Now, in a regular polygon, any regular polygon can be circumscribed by a circle. So all the vertices would lie on a circle. And that means there is that center point. That center point is equidistant from all the vertices of the regular polygon. It's equidistant from all the vertices of the regular polygon. Now, all those are going to be radii of the circle, but they're also called radii of the polygon. So in a regular polygon, the segment from the center to a vertex is called the radius. And now if we look at this regular polygon, the radii divides into 5 triangles. And we've worked plenty with triangles, so the area of the pentagon would just be 5 times the area of the triangle, because all the triangles are congruent by side-side-side congruence. And all the triangles are isosceles, so that angle's congruent to that one. And since they're congruent, that angle's congruent to that one, congruent to that one. And all of these are congruent angles. So if we can find the area of one of these triangles, we can find the area of the whole pentagon. So I'm going to take one of those triangles onto a new slide, or whiteboard, whatever. You guys get it. So we have that isosceles triangle. The two radii, the side length, and we know the area of a triangle is 1/2 base times height. So for this one, it's going to be 1/2 s, and we need to find out this height. I'm going to use the variable a. And why I use the variable a will be clear shortly. So 1/2 times s times a is going to give us the area of this triangle, because a is that height perpendicular to the side length. Now we're able to find out the values of these angles, the measures of these angles, because since each of these is one of those, well, those would be two congruent parts of one angle, so each of these would be half of that angle measure. Hey, we know how to find an angle measure in regular polygon. It's 180 times n minus 2 all over n. So 180 times 3 is 540, divided by 5 is 108. So that would be the measure of each angle in the pentagon. So this would be half that. And that would also be 54, because it's isosceles. And these two add to 108, so this whole thing up here is 72. So, since it's isosceles, this altitude is also the perpendicular bisector of the base. So that's s over 2. So if you knew the side length of your pentagon, you'd be able to find out what this altitude is, what that height is, just using tangent. Tangent of 54 equals a, because a is opposite, over s over 2. So a equals tan 54 over 2. Just kidding, it's s times tangent of 54 over 2, not stan. So this would be that length of the height. So the area of the triangle, I'm not just going to rewrite that every time, because that angle is going to change every time. I'm just going to leave it as a. So the area of the triangle would be this. So let's go back to our pentagon. So that's a. Now the reason I chose the variable a is because what that distance is called. The distance from the center to the midpoint of a side of a regular polygon is called the apothem. So it's called the apothem. It's not the apothem. Apothem is what you call roadkill when you bite your tongue. This is the apothem. So that's the apothem. That's the height of this triangle. Well, the area of the triangle is 1/2 times s times a. Well, this is all just multiplication. So I'm going to move some things around, since multiplication is commutative and associative. So 1/2 times a, and I'm going to group the 5 and the s together. Oh, so s is the side length. There's 5 sides. So 5 times s is just the perimeter. So the area of this pentagon, it's 1/2 times the apothem of the pentagon times the perimeter of the pentagon. And if this wasn't a pentagon, let's say it was a hexagon, it wouldn't be 5 triangles, it'd be 6 triangles. So then it'd still be 1/2 times the apothem, because the height of the triangle would still be that apothem, except it'd be 6s, which is still the perimeter. Or, if, say, it was a 32-sided polygon, a triaconticadigon, then it would be 32 triangles. But the height of those triangles would still be the apothem. And it'd just be 32s. So it's still the perimeter. So in general, this isn't just the area of a regular pentagon. This is the area formula of a regular polygon. And this works for any regular polygon. All right. Have fun, everyone. See you next time.